Hello class, this video is all about application of first order ODE, focusing on Newton's law of cooling and exponential growth and decay. At the end of the lesson, students should be able to solve problems regarding decomposition or growth using a differential equation. Second, solve problems applying a differential equation involving Newton's law of cooling. Last is solve problems using calculator technique. Let's start with Newton's law of cooling. Newton's law of cooling states that the rate at which a body cools is proportional to the difference between the temperature of the body and of the surrounding. When we say rate, that is the derivative of a quantity with respect to time. And the quantity that is changing here is the temperature. So, our mathematical equation for the rate is derivative of the temperature with respect to time. And it is proportional to the difference, between the temperature of the body and of the surrounding. So, temperature of the object and the temperature of the surrounding. Difference of the temperature of the body and of the surroundings. So, to transform this one, this becomes equal and we add proportionality constant. Then we copy t minus ts, derivative of t over dt. So, this is now variable separable. So, first we have to get rid of the denominator. So, we will multiply both sides by dt. And this becomes d capital T equals k t minus ts dt. Next is we divide both sides by t minus ts. So that this will be multiplied to its derivative. So if we multiply 1 over t minus ts to k times t minus ts dt, t minus ts is cancelled out, right? So only k times dt. And if we multiply dt to 1 over t minus ts, it becomes dt over t minus ts. So, it is now arranged. Then, we can integrate. The integral of dt over t minus ts is ln t minus ts equals, we copy the constant k, then the integral of dt is t plus c. To eliminate ln, we will use e, both sides. So, e and ln cancel out, so we only have t minus t sub s. And using the law of exponents, x to the power of m plus n is equivalent to x to the power of m times x to the power of n. So, this one is equivalent to e to the kt times e to the c. But e to the c is constant, right? So, e to the kt times e to the c is c. And c times e to the kt is c e to the kt. But we have arbitrary constant. So, we will apply that time equal to 0, and that is when the temperature of the object is equal to the initial temperature of the object. So, when the time is 0, t is equivalent to t sub o minus ts equals c e to the k, then time is 0. 0 times k is 0. E to the 0 is 1. 1 times c is c. So, the equivalent of our arbitrary c is to minus ts. Then, we replace c, this one. So this is T minus T sub S equals, C now is T sub O minus T sub S e to the kt. So this is now the general solution of Newton's law of cooling. So T is the temperature of the object at any time T. T sub S is the surrounding temperature. It is a temperature that is constant. T sub O is the initial temperature of the object. K is the proportionality constant, and the small t is the time. So how to solve Newton's law of cooling problems? So first, you write the given and what is asked in the problem. Next, you find the proportionality constant by applying it to the formula with given time and temperature. Last is to find what is asked by applying it to the formula with a given unknown variable, time or temperature, and other given quantity, time or temperature or population. So first, write the given and what is asked. Next, find the proportionality constant K. Then, find what is asked. So let's have some examples. Number 1. A body of temperature 160 degrees Celsius is immersed in a liquid of constant temperature 100 degrees Celsius. So, what are the given from that statement? (160°C) is the initial temperature of the object. So that is when the time is equal to 0. The constant temperature 100°C is the surrounding temperature. T sub S is constant. So 100°C is surrounding temperature. If it takes 2 minutes for the body to cool to 140°C, after 2 minutes, T sub 2, T sub O is when the time is equal to 0. T sub 2 is when the time is 2 minutes. So at 2 minutes, the temperature is 140°C. How long does it take to cool to 120°C? So we are looking for the time. So time is missing. So T sub X. So our formula is T minus T sub S equals T sub O minus T sub S e to the kt. So we are done with the first step. Find the given and what is asked. Next is to find the value of K. So we will apply the time at T equals to 2 minutes. We will not use T equals to 0 because we already used that in finding the general solution, right? So we start at 2 minutes. So at 2 minutes, the temperature of the object is 140 degrees. So what is the temperature of the object at 2 minutes? The temperature is 140 degrees, right? Minus the surrounding temperature is 100. Equals initial temperature is 160. Minus surrounding temperature 100. E to the K times the time is 2 minutes. Then we subtract. 140 minus 100 is 40. 160 minus 100 is 60. E to the 2 times K. Our purpose here is to find the value of K, right? So first, we have to get rid of 60. Next is E, then 2. So first thing is to get rid of 60. So divide both sides by 60. So if we multiply 40 to 1 over 60, the result is 2/3, right? 60 divided 60 is 1. So e to the 2k. So to get rid of e, we will use ln, both sides. So the result is 2k ln 2/3. And divide both sides by 2. So this becomes 1/2 ln 2/3 equals k. So we have now our k. Then we will find what is asked. So let's apply at T equals to X, unknown. The temperature of the object is 120 degrees Celsius. So what is our T? T, when the time is X, T is 120 minus, what is our TS? TS is 100 equals T sub O is 160 minus TS 100 e to the k. Our k is 1/2 ln 2/3, right? 1/2 ln 2/3. Then multiply to x. 120 minus 100 is 20. 160 minus 100 is 60. Then e to the 1/2 ln of 2/3 times x. First, we have to get rid of 60. Next is the exponential, then 1/2 ln 2/3. So that we will find the value of x. That is our time. So, we have to divide both sides by 60. So, 20 divided 60 is 1/3. 60 divided 60 is 1. So, we have e to the 1/2 ln 2/3 times x. Then, ln both sides. So, the result is 1/2 ln 2/3 times x. Then, divide both sides by 1/2 ln 2/3. So, ln 1/3 divide 1/2 ln 2/3 equals x. So, using our calculator, ln 1/3 over 1/2 ln 2/3. The result is 5.419 minutes. So this is the result. So how to use our calculator to check if our answer is correct? Get your calculator first. Then you start with mode. Then stat. Then e to the x. You choose that one. So here, mode, stat, then e to the x. But to this calculator, that is e to the bx. Then we will have this x and y. So what will you write in x and y? Our x is the time, and our y is t minus t sub s. So when the time is 0, what is our temperature? When time is 0, the temperature is 160 minus Ts. 160 minus Ts is 100. So we will input 60. Next data is when the time is 2 minutes, the temperature is 140. When the time is 2 minutes, the temperature is 140. Minus the Ts 100, so you input 40. So when you're done inputting the data, you tap AC, then shift 1. Then choose reg. Then, you only choose X bar or Y bar. You choose X bar. Choose X bar when missing is time. Choose Y bar when missing is temperature. So for this example, the missing is time. So we will choose X bar. Then you multiply that to T minus Ts. So the temperature of the object at missing time is, at missing time, the temperature is 120. So 120 minus Ts, 120 minus Ts, Ts is 100. So first, input 0. Next is 2. Here, 60. Next, 60. 60. Then 40. So when you are done inputting the data, AC shift 1. Then you choose regression. So for this calculator, I will choose this one, regression. Then when the missing is the time, so choose X bar, so this one. Then you multiply that to 120 minus 100. 120 minus 100. So the result is 5.419. minutes. Okay? So that's it for calculator technique. So next example. Suppose that an object initially having a temperature of 20 degrees Fahrenheit is placed in a large temperature-controlled room of 80 degrees Fahrenheit. And 1 hour later, the object has a temperature of 35 degrees Fahrenheit. What will its temperature be after 3 hours? So the answer must be 55 degrees Fahrenheit. So let's write the given. Suppose that an object initially having a temperature of 20 degrees Fahrenheit. So the initial temperature of the object is 20 degrees Fahrenheit. That is when the time is equal to 0. It is placed in a large temperature-controlled room. So meaning the temperature is constant. So 80 degrees must be the surrounding temperature. 1 hour later, the object has a temperature of 35 degrees Fahrenheit. 1 hour later. So T1 is 35 degrees Fahrenheit. What will its temperature be after 3 hours? So after 3 hours, missing temperature. So we will use the time equal to 1. So our formula is T minus T sub S equals T sub O minus T sub S e to the power of KT. So at T equal to 1 hour, the temperature is 35 degrees Fahrenheit, right? So at T equal to 1 hour, the T is 35. Minus Ts is 80. T sub O is 20. Minus Ts, 80. E to the K, then the time is 1. 35 minus 80 is negative 45. 20 minus 80 is negative 60. Then 1 times K is K. So first, we have to get rid of negative 60, then E, then find the value of K. So first, we will divide both sides by negative 60. So negative 45 divide negative 60. 45 divide 60 is 3/4. Then e to the k. Then get rid of e, we will use ln both sides. So k is equivalent to ln 3/4. Now that we have the value of k, we will find the temperature now. So at t equal to 3 hours, T3 is missing. So what is our temperature at time 3 hours? T3 missing. Minus Ts is 80. T sub O is 20. Minus Ts 80. E to the k, k is ln 3/4. Times time is 3 hours. So, transpose negative 80 to the right side. It becomes positive 80. 20 minus 80 is negative 60. Then copy e to the ln 3/4 times 3. So just input that to your calculator. 80 minus 60 e to the ln 3/4 times 3. Answer is 54.69 degree Fahrenheit, or approximately equal to 55 degree Fahrenheit. So that is the temperature after 3 hours. So how will we use our calculator to find the answer, or to check our answer? So it's same. Mode, stat, then e to the x. Then this will appear. X and y. X is the time, y is t minus ts. Make sure that the data that you will input here must be positive. If the result is negative, just swap t and ts. Okay? So at t equal to 0, what is the temperature? 20. Ts is 80. So at t equal to 0, the temperature is 20, right? And Ts is 80. So we will input negative 60. But I told you a while ago that you must input here a positive. So we need to swap t and ts. Ts minus t. So that the result is positive. 80 minus 20. So the result now is positive 60. Next, when the time is 1 hour, temperature is 35. When the time is 1 hour, temperature is 35. So Ts is 80 minus 35. So 80 minus 35 is 45. Then AC, shift 1 and choose regression. Then you choose between X bar or Y bar. When the missing is time, choose X bar. When missing is temperature, you choose Y bar. But for this example, the missing is, what is missing for this example? Temperature. So missing is temperature. So we will choose Y bar. Then multiply that to the time. So, we are looking for the temperature when the time is 3 hours. So, times 3. So, let's use our calculator. Mode, stat, e to the x, but for this calculator, that is e to the bx. So, we will input 0, 1, 60, then 45. Then AC, shift 1, choose regression, this one, for this calculator, and choose y bar. And multiply that to 3. The result is 25.31. Remember that y bar here is TS minus T. So, the result for TS minus T is 25.31. And you are looking for this one, T. So, transpose T. So, this becomes positive. And you transpose 25.31 to the left side, it becomes negative 25.31. So, what will be our temperature? TS is 80, right? 80 minus 25.31. 80 minus 25.31 is 54.69, round off to 55 degree Fahrenheit. So, we have now our answer.